let's take our first look at an example of a LaGrange multiplier. We're going to have our objective function f be 2x squared plus y squared plus 2. And we're going to constrain it so that x and y must lie on an ellipse C, given by g equals x squared plus 4y squared minus 4 equals 0. So 2x squared plus y squared plus 2 is some function. We're going to overlap that function with the ellipse x squared plus 4y squared equals 4, and see where those points must cross. Okay. So what we're looking for, remember, we're trying to set the gradient of f equal to lambda times the gradient of g. So let's find the gradient of both. The gradient of f dx dy, or ddx and then ddy times this gives us 4x and 2y. When we do, remember, the gradient is this. So we're going to hit ddx and ddy times g, and we get 2x and 8y. And we want to set these equal to each other. So we got to set them equal to each other component-wise. This is our I hat direction, our j hat direction, and we're going to match those up, I hat to I hat. Okay. So if I equate the i's, I've got 4x equals lambda times 2x. And if we get them all on one side, factor out an x, since the right side is 0, we can use the zero product rule, and either x equals 0 or lambda equals 2. And I can do the other side, and I equate the j hat vectors, not vectors, well, yeah, the j hat components, and we've got 2y equals 8 times lambda y. And we do the same process, and we get y equals 0 or lambda equals 1/4. Now we've got two options. Let's just focus on on this side over here. X equals 0 or lambda equals 2. Let's check out what happens with both. So if x equals 0, then our constraint function, x squared plus 4y squared minus 4 equals 0, turns into just 4y squared minus 4, and it's set equal to 0. So when we solve for 4y squared minus 4 equals 0, we get y equals plus or minus 1. That isn't 0 anywhere, so our g isn't 0. Which sounds weird. So with y not equal to 0, because that was this one. If we had x equals 0 and y equals 0 together, then they would go together, but they don't. So x equals 0 must be going with lambda equals 1/4. Okay. So these two go together. And this is going to generate some points right here, right? I've got 0, 1, and I've got 0, negative y. Okay. Now let's take a look at lambda equal 2, and we're going to see that we should get the y equals 0 to pop out. Let's just check. If we have lambda equals 2, I plug it in over into this equation. I've got y times 1 minus 4 times 2, or this effectively becomes negative 7y equals 0. So y has to equal 0. And sure enough, that matched up. I've got lambda equaling 2 matches up with y equals 0. And so what happens if I set y equal to 0 on our constraint curve? Because that's telling us where we're at. If I plug in 0, we got x squared minus 4 equals 0. So x has to equal plus or minus 2. And we have 2, 0, and we have negative 2, 0. These are all the points where the gradient of f and the gradient of g are some scalar multiple of each other. So let's take a look at what we have. If we look at A, where we had x equals 0, we plug in both of them, and we're going to get into our function f. We're trying to find out whether we have a maximum or minimum f, because remember, it's an extremum there. And we plug it in and we get a 3. And then we do the same with B, and we plug in our 2, 0 and our negative 2, 0. Lambda isn't, even though we have lambdas assigned to it, it doesn't really play a factor anymore. It just helped us figure out what that scalar multiple was and that it existed. If we plug in 2 or negative 2, comma 0, we get 10. So we have a maximum value at plus or minus 2, comma 0, and we have a minimum value of f at 0 plus or minus 1. And so the max is 10, the min is 3, everything else is somewhere in between for f in that region. That's our first example. So G and F lined up there. And that's it for this video. We'll do another example in the next one. Peace.